It says request host permission.
But is there no option to record the session?
There is. So if I click the button, it says, please request recording permission from the meeting host.
I see. So just in case, can I actually nominate you in case I forget recording? Because last time we went through like 2 hours and then I
Mhm.
forgot that I started
Yeah.
recording. So in case, just to bring it up, in case if I forget, I've started recording now,
Okay.
but I think in the future we will. In
Right.
the future, we will, yeah, ensure that at least one of us is recording.
Okay.
So I just flew back like 1 hour back. So I'm in Seattle, back in Seattle. So I wanted to take the class yesterday, but I think a few of them had work, so I decided I'm going to fight my jet lag for like 3 more hours and then crash.
Yeah. How did your engagement and everything go?
Went well. It was a pretty grand affair. I didn't expect it to be,
Okay.
but so many people to come. It's quite contrary to how things are here, right? Here
Yeah.
it's a very private affair between the boy and
Yeah.
there it is the boy, the girl's family, the boy's family, their families, their family.
Yeah.
So it was like a regular Indian. Let's just give 5 more minutes for
Yeah. Sure.
everyone else to join. So Meher, did you get a chance to like code up PCA? Meher, can you hear me?
Hi, this is Raghav.
Hi Raghav. Did you get a chance to do the PCA assignments and stuff?
No, no, sir. I don't know. Like, I've been lagging so behind.
Oh, okay.
Trying, but I'm unable to focus. Like, I started a small research team in India.
Oh, okay, okay.
So
But if even if that is not the case, please go through the video lectures again, uh,
yeah,
just in case, because you know it will be helpful. Last time I forgot to record, but I actually then re-recorded the session,
true.
went through the code also what we have. So I just was I think Satya actually did it. I think Deepika, but I didn't get anything from Meher, so I was just wondering you if you and Meher were able to uh, run the assignment and stuff. So.
Yeah. So what I'm going to do is this Friday, entire Friday, I kept free for myself. So no work on Thursday night and Friday throughout the day.
Okay.
So I'm going to do it on that day.
Okay, perfect. Um, so today we're going to do support vector machines, which is one of the uh, like one of the most important uh, classification algorithms. So until now, just to recap, we have done k-means, which was unsupervised machine learning classification problem, and then we did feature engineering work on PCA eigenvectors and stuff, so which actually is utilized to reduce the dimensionality and uh, and actually choose features which are more relevant to us. So I think as we do in every class, I'm going to give a quick recap of what we have done yeah, in the last class. So it'll be a little fresh for us. So last class, so we had so we went through PCA or principal component analysis. So in principal component analysis, the main thing which we had to see was how do we transform. So what are the two main things while choosing feature sets? Like when we take a problem, we extract the features, right? So I was mentioning that these features need to satisfy two main criteria. What are the two main criteria?
They should be linearly independent.
Yes, that is one.
Yeah.
And what is the other one?
There should not be any. Um, I mean, it should be clean to that extent that it has zeros and bits and bytes.
Yes, so that is one. So they have to be linearly independent for the determinant to be non-zero. But then there was one more criteria which I mentioned last time. So when you are taking features, we need features one which are linearly independent. What is the second one?
To have variance.
Exactly. So the features you need to choose such features such that they have the maximum variance. So these are the two main things which we need to do in feature engineering before we pass it to any algorithm. Because the higher the variance, the more information we get about that particular observation. So for example, I was like one example which I was giving was the housing example. So let's say we have two features. One is the square footage of the house, and another is the cost of the house. And if the cost of the house is varying a lot, and the square footage is not, then a more important feature set or more interesting feature set would be the cost of the house. Because if the square footage is pretty much the same, but the cost is varying, that means that there is something else, like maybe the locality of that particular house or something is what is affecting the data. So we always need to choose features one, which are linearly independent. And the second criteria for choosing the feature set is they should have the higher variance. So it is physically or like humanly not possible. So let's say we have, so nowadays what happens is we take a lot of features, right? So so first set is basically we try to get as many features as possible for any observation. And that's what happens in your day-to-day work life too. So you go to a thing and let's say they give you some sales data or something and they say, hey, this is all the data we have. So then come up with an algorithm. So not all the features or not all the data which you get is useful for the machine learning algorithms. So what we do in such cases, we do principal component analysis. Principal component analysis helps us solve these two problems by actually, so what principal component analysis does in a gist is it tries to take all the features and it tries to compute the eigenvectors of that particular feature. And then it tries to look only those components in the eigenvector space which actually have non-zero eigenvalues. So higher the eigenvalue, it's higher the variance, right? So that was one of the main features which we saw. So when we looked at eigenvalues and eigenvectors, why did we actually choose to do eigenvalue decomposition? Is because, let me show you that. Yeah. So what we have seen is like two things. When we actually have, so let's say the reason we looked at eigenvector space is because these eigenvectors actually is a transformation of this feature space into the eigenspace. It'll give us only those features which are relevant or which have higher variance. And how do we know which feature has higher variance? The eigenvalue of that particular eigenvector will be high. If the eigenvalue is high, then that particular feature in that eigenvector space is more relevant. And that's what we have seen, that when we actually did the eigenvalue decomposition, if we took the top three eigenvectors, by top three, I meaning the three values for which the eigenvalues are really high, it captures most of the information than the features or the eigenvectors for which the eigenvalues are relatively low. So the eigenvector decomposition transforms this feature space. Let's say we have 200 features, and these features can be all jumbled up. It need not be linearly independent and stuff. But when we do an eigenvalue decomposition and we look at the non-zero eigenvalues, so one property which we saw that is like if at all we have P, if the rank of the matrix is P, then P eigenvalues will be non-zero and n minus P will be zero. So this means that those n minus P features are irrelevant to us. If that means that that constitutes of all the linearly correlated stuff of data. So we only look at the p eigenvalues, and even in these p eigenvalues, we take the top, like top, depending on what your speed criteria is and stuff, we take the top k values for which the eigenvalues are relatively high. So what we have seen is whenever we take these top k values for which eigenvalues are relatively high, they capture most of the information about the data. So that's why doing a principal component analysis helps us understand the data much better. And once we look at the data in the eigen vector space, we are going to only choose those features for which the variance is high and they are linearly independent of each other. So the two main things which feature engineering requires is solved using PCA. So if we didn't study PCA, we could do this manually also by actually computing the rank of the matrix and then trying to manually find, by doing linear, by doing a guesswork that, well, let me take feature 1, 2, 3. Now let me see if this is linearly independent, or else take the features 3, 4, 5. So in case of, let's say, Indian liver patients, we had 10 features, right? Luckily, the matrix rank was 10. But what could you do if the matrix rank was 8? It means that there are some sub features which are linearly dependent on the other features. So you will probably do some guesswork as to, I'll take 1, 2, 3, 4, 5 up to 8. So maybe those would be linearly. So now you don't have to bother about picking those features and stuff. What you do is you take all the 10 features, do eigenvalue decomposition, or just call PCA. In PCA, it'll give you the first thing you will look at is eigenvalues. In eigenvalues, look to see which one have the highest eigenvalue percentage, and just take only that, because most of the data information, the higher the eigenvalue, higher is the variance. So if you have like eigenvalues which are relatively really high and then eigenvalues which are relatively really low, you can totally omit those eigenvectors for which the eigenvalues are very low, because they don't contribute much to the information, because the variance of that is relatively low, and we only pick the ones which have the highest variance. Now when you do that and then you find new principal components, then you can just utilize those principal components for your analysis. So I actually recorded another video. I hope you guys have looked at it, and I've sent this thing. So in this case, in the last is there a so some Meher is asking, is there a specific cutoff value for picking the highest number of eigenvalues? So Meher, so there is no specific value, but it so that's why I had this function eigen percentage. So basically, let's say you take the first eigenvalue and it contributes to 23% of the data, and the second eigenvalue, both 1 and 2, will contribute to 50% of the data. Third one contributes to like another 20%. So you have to pick, it's up to you. If you can capture 70% of the data using 3 eigenvalues, eigenvectors, then do that. If the others ones are contributing really less information, like compared to 23%, if the other one is contributing only 3%, you can totally ignore it. So it's totally up to in your hands. So, but then ensure that you don't leave an eigen value or a principal component which actually is contributing a lot of information. Again, it's all relative, right? So in this case, we have seen here, when I ran this code, let it run for a bit. So this function which I had, like eigen, okay. So I shifted the laptop onto cancel. So in this case, when I calculated the eigenvalues, I showed the percentage increase in each when you take each eigenvector, right? So when you run this, so you see that. So here, so when you run this here, you see that the first one, when you take it, contributed to 23.84%. When you added two of them, it contributes to 37%. So that means the second eigenvector is contributing 14%. The third eigenvector is contributing 10%. So this is the percentage increase of the amount of information which is contributed. So if you look at this, in the last few things, like 85 to 90, 90 to 96 to 100 to 100, that means definitely these two are not contributing to anything. That means they'll be zero. And even in this case, this is contributing only 6%, and this is contributing like 1% and 5%. So depending on your choice, like I would suggest, like if you can take the eigen values which can contribute to around 80% of the data, I think you should go ahead with it, because that is because you will have lesser number of features, more rich features, and you already capture like 80 to 90% of the data. If the eigenvalues are relatively very less compared to the higher eigenvalues, then you can easily omit them because they don't contribute. You can still take them, but it's of no use because the amount of computation you need to do for 3 to 4% increase is minuscule. So that's why there's no fixed number. It's based on your observation. First thing when you do is when you actually look at the data and compute its eigenvalues, and you see that the 3 or 4 eigen values are relatively very high, you just take the first 3, 4 principal components. So in this case, I'll just do a quick recap. So what I've done in this case is, you have seen someone was asking me like, oh, there are only 8 of them, because I think I've mentioned that here, because you can, if you look at the principal components, these 3 of them are the same. So 0.6935, 0.123 So these 3 are the same. That's why they are looking as the same document. So that's why all 3 of them will lie around 0.6, around here. So what I've done in this case is just shown you what the principal component looks like. So if I just take one principal component, how does it look? Like you can see that the data variation is really high. So this one, I purposefully put this in 2, but then if you look at this, this is the one which actually has both cats and cars. So if you look at the eigenspace, this is very, very far. So if you just do a k-means on this, you will get this as one cluster, this as another cluster, and this as a third cluster. So you can use, k-means on, you can use for grouping, you can again use k-means on these principal components to classify the documents. But as such, principal component analysis is not a classification algorithm, it's just a feature algorithm. It does, all it does is makes you choose features which actually again have higher variance and linear independence. So this is how it looks when you take only the first principal, so first and second principal component. But then I think in the other one, I took the 3 principal components. You can, I don't know if the colors are visible properly, but you can actually plot. You can do if you do 4, it's really difficult to visualize, but that's what I've done in this thing. So I took first and second principal component, and then in the second case, I took the third principal component. So the other good thing about this, so there are, so this is the one which is using PCA components directly, but remember how PCA is, how PCA does it. It uses SVD to actually get it, because SVD is a generic version of eigenvalue decomposition for an n by n matrix, because eigenvalue decomposition can only be done for square matrices, and SVD actually will do it for n by n matrix. So there's a slight difference between both these programs. I thought I'll just highlight that once, because in SVD what I've done is I've manually done what PCA does. So I've taken the array and then sorry, in PCA, not SVD. This particular file in PCA, this is my custom PCA. That's why I did PCA.py. The other one is utilizing the sklearn's PCA library. So in this particular PCA.py, what I have done is I purposefully took, I calculated SVD myself. So I took the SVD myself, and then I said, hey, in the SVD, the S is the matrix which actually has the eigenvalues, right? So if I want to see only how first principal component works, I'm going to actually just use S of 0 and make everything else as zeros. So that will take the first principal component. And that's why I've computed the U reduced, V reduced, and S reduced. And I recomputed that. So I remultiplied all of them. So this is what will give you the first principal component, because I've made everything else 0 here. And then I printed those values out, and you can see this here. So if you have to do PCA yourself, then you need to do SVD yourself. In SVD, you take the S matrix and then choose the first or second or third, uh, whichever components you want. In this case, I just use the first principal component. So if you take the first principal component, this is what the principal component looks like. You can see that this one is really way far away, and then these ones are like, so you can see that obviously there's a clustering here. You can see that all these belong to cat, these belongs to cars, and then this has both cat and car together. So this is just to show you like how the first principal component looks for all the 12 documents. But then there is one small thing which I think I have to mention it again. So this, when I did SVD myself, I took the first principal component and then re-multiplied everything together, right? But if you actually are doing PCA, this is the small thing I wanted to mention. I don't know how many of you have observed this. So what I'm doing here is I'm taking the principal so PCA dot components gives me only the axis information. It doesn't give me how much value of that particular feature is on that component. So you see this data, I did this thing called data dot PCA component. The reason for that being the dot product always gives you how much, so this goes back to the matrix lecture. So that's why I was actually spending some time on vector products, dot products and stuff. So if you look at the dot product, so AB cos theta, right? So here, the formula AB cos theta is the dot product, can be interpreted as the product of the magnitude of this thing. So it is basically the component. So when you take A, B cos theta, that is basically saying the projection of that onto this vector. So now the principal component is only giving me the eigenvectors, right? But I need to know what the value of what the value of that particular is on this particular vector. So that's why I did the dot product here. So that is the one small difference which you need to do if you actually are doing PCA using sklearn library. So when you're using the sklearn library in PCA, what you do is first you actually calculate, you first see what the eigenvalues are. That is given by explain variance. So when you do explain variance, I'll give you the eigenvalues. But then PCA.components will only give you the principal component, the eigenvectors. So in order to find the value of that component, you need to take the data and project it onto this particular eigenvector. So that will give you the exact value. If you're doing it directly using SVD, when you multiply it, it will directly come. So in this case, you see that when I multiplied A reduced with this thing, I already got all the values in A reduced. But if you're using the sklearn library, you have to do the dot product to get the principal component. Is this thing clear? Any questions on this? Please let me know. I think I tried to explain that as much as possible in the previous lecture, but then it was just me talking to myself, so I didn't know how that thing went because I was not hearing any questions back. But everyone clear on what PCA is? How do you compute PCA components? How do you utilize PCA for like dimensionality reduction and stuff? I hope those graphs or the charts are helpful in visualizing what the component does. Like first component, how does it look? Second component, how does it look? When you take 3 components, how does it look? Any questions on this or on the code or anything so far? The only thing I wanted to mention is when you are actually using the sklearn library, when you do PCA.components, this will only give you the eigenvectors. You need to take your data's dot product onto that vector. Questions? Yeah, I can do that. Let's see if, depending on time, so I think Meher is asking, like, is it possible to type the code along with this? I was actually thinking of doing that because in that way, then we can, but I don't know if we'll have enough time to like write the code, everything in the class. Let's see. I think from future classes, at least for SVM today, we'll do that. We will type the code along with the class. and then we will do it. Any other questions? Deepika, any questions?
No questions. I only thing is it was a little more to take in the data and all, but I just used your videos and it was very helpful.
Yeah, so I think the coding maybe. So the first thing, I'm not paying so much attention to the code because this is one way to code it. You have like if you learn R, right, you can use R libraries and stuff to code it. This is like just as a reference of the code which you need. But main thing is understanding the concept of when to use PCA and what is the math behind it, and like if you do PCA, what are we getting? And the other thing is visualizations. I'll try to write the like this time. I think we are going to do support vector machines today. So we'll write the code along with the thing, but there are subtle things which are different when, because this one has like too many things, right? I did SVD, and then I did so SVD is basically uh, what PCA uses this thing. So I tried to do both if you want to do SVD and if you want to directly use the library. But when I was actually recording it again and explaining the code, then I thought maybe I should have mentioned this thing that when you're doing PCA, the PCA will only give you the component. That is the eigenvector. So you have to take the dot product of the data with that particular component to get the exact value. But when you do SVD directly, when you multiply it, so you see you multiply all the three, right? You get your actual component. In case of PCA, it will only give you the eigenvector direction. So you have to take the dot product of the data. So that is one additional thing I wanted to mention. And rest of them are, so these are just for visualization of how the first component, second component, third component look like in the eigenspace. And you can clearly see when I took the cats and cars example, you can clearly see the two main components of it is one is cat and other is car. And there is one statement which has both cat and car is like way away from if you take the first component itself, it's like way away from the regular data. So you see this is the one here. So this is the class 2. So it is way away from the data. So you can see how how this principal component values actually look like for each of the dimensions. So for cats, it gets clustered here. For cars, it gets clustered here. For both of them, it is way away. So it's a good way to visualize how principal components work. So having said that, I think I'm going to spend enough time on this thing. So this is again, and I was actually mentioning, I actually gave Satya the thing like from now on, if even if I'm not recording, right, like at least let me know, because last class we actually went to good 2 hours and then I realized I did not record. So this time if I'm not recording, you can request to record yourself as well. That way we'll have a recorded session. So if it is clear with what we have done in PCA and with the cars and the cats example, I'm going to like start this another algorithm today. This is like probably before so we're going to learn about support vector machines today. Support vector machine is like probably like one of the most critical algorithm used for classification. So the use of support vector machines is secondary. So I would rank like deep learning the first, or I mean depending on the data. But everyone like now with the recent research, neural networks or deep learning is being used as the first algorithm for classification. I'll tell you about that why when we do neural networks. But after that, I think um, at least from what I have seen is for classification. Again, it depends on the data. Today we'll see when we will use support vector machines. Like depending on the data, support vector machine has a very large base of classification algorithm. You will see that being used in a lot of places. So uh, probably in all the algorithms, the most math intensive algorithm is support vector machine. So we'll go through it slowly. Again, I want you to understand what it does. Even the math here is probably what you learn, not even in masters. Like if you take like core mathematical courses, that's when you will understand everything here. I've captured most of it, but don't worry if you don't understand the whole math. Uh, just understand what it does, because you don't need to do. All you need to do is basically when you call the support vector machine function, you need to know what are the parameters you need to change there and how that is affecting. You don't need to go into the complete math of it, but I'll try to do a good job explaining how the math behind it works. So before we start support vector machines, I just want to okay. So we have seen the main classification problems, right? So main categories of problems: machine learning classification, prediction, anomaly detection, and reinforcement. So these are the four categories of problems. Reinforcement learning, anomaly, these are all small problems. Like there is a small niche areas where these two get used, but main problems which uh, we come across is classification and prediction. These are the two main class of problems which machine learning tries to handle. And SVM is another very important uh, classification algorithm. It's a supervised learning. That means you need to have the label. So in unsupervised, we only did k-means so far. Everything else which we'll do is supervised. There's one more clustering algorithm called hierarchical clustering. We will, if time permits, we'll do that in the later on classes. But as far as unsupervised learning goes, there are two main algorithms for unsupervised learning. That is k-means and hierarchical clustering. So, but let's not get into like. So we've already finished k-means, but when supervised, most of the algorithms are supervised, because in supervised, you're telling the machine what each observation is. It is much better if you have labels. So if there's an option between supervised and unsupervised, always go for supervised learning, because it'll give you much more information about each observation, and it'll tell you what each label is. And in supervised machine learning, SVM is like one of the so I would rank it second best algorithm for nonlinear classification. I will talk about that a little further today. But before that, I let me actually bring up the. So I will repeat this every class. So let's say we have an observation with 10 features, right? So we have 10 features, like let's say Indian liver patients only. Indian liver patients. We have 10 features. So what will each observation be in a 10-dimensional space? If we are taking 10-dimensional
Points,
space,
right? 10
then it'll become point, not 10 points. Each
Oh,
observation
sorry,
will become 1 point, right? So always when you are doing a machine learning algorithm, that is the first step. First is feature extraction. In feature extraction, relevant features, use PCA to get those features. But once you have PCA, let's say you decide that I want to use 5 principal components or 10 principal. Let's say we are using 10 principal components, right? So that means that we'll take 10 dimensions. Now, once you have each observation with 10 dimension, always go into 10 dimension space, because every observation has to be a point, because that's when we will understand what the machine is doing. So in let's say in 10 dimension space, everything becomes a point. And then we saw that even in k-means, if we can see that if there are two clusters, how will it get clustered? So let's say there's one cluster like this and another cluster like this. So there, let's say we're doing a two-class classification. So there's two-class classification, and then they look like this. So now I think in case of k-means, we have seen that it will actually create a cluster like this and cluster like this. So basically, and if a new data comes, the test data comes, it sees which cluster it falls under, and that's when it will tell you whether it belongs to class 1 or class 2. That's what you have seen in k-means, right? So let's say I'll give you a. So technically, I think we even spoke about this last class also. What is meant by machine is learning this data? So when I say when a machine learning algorithm is finished training, what is it that it's doing with this data? Whether it be k-means, whether it be support vector machine, whether it be anything else, what is it trying to do with this data?
It is actually prescribing how the data logic should be.
That is one, but a better way to put that is it is learning the decision boundary. So I think even in Indian liver patients we saw that Indian liver patients were somewhat like this, right? So there were like a lot of things like this, and then there were like crosses across like this. So we saw that if we draw two lines and then if we say that anything within this box, if it falls, because the training is telling me that these people don't have disease and these people have the disease. So we saw that this was the decision boundary. So whenever we say that the machine learned the data, it means the machine learned the decision boundary, nothing else but the decision boundary. In this case, it learned these two equations of these two lines, so that when the next time when the new test data comes, it will see which side of the line is the observation on, and then it will tell you whether that is having a disease or not having disease. So even in this case, if the data is like this, when we are telling the machine, hey machine, learn this data, that means that the machine is somehow coming up with a decision boundary. Now the decision boundary in this case was linear, right? It is like this. Decision boundary need not always be linear. It can actually come up with an equation which is like this. So this is the equation of the line which the machine learns. So once the machine learns this, then we don't care about all the training data. This is all gone. This data is only helpful to create this decision boundary. So once this boundary is actually learned, then we say the machine learned this, and then we'll start testing the data. When you give the test data, it will see which side of the boundary it lies. If it lies on this side of the boundary, it says class 1. So let's say this is class 1 and this is class 2. So once it learns it, it will tell you that if the test data falls on this side, it's class 1. If it falls on the other side, it's class 2. So basically that's what happens, right? So whenever we say that the machine is actually learning the data, that means it is learning the decision boundary. So this is like the fundamental thing of what machine learning does. So in some cases, like in this case, it need not be a non-linear line. It need not be a curve. In this case, it can simply be a line, right? So if I draw a line like this, so this is a linear boundary, right? Because it can be expressed as ax plus b, linear boundary. So I think the point I want to make is this decision boundary can be linear, it can be non-linear, it can be polynomial, it can be any kind of a boundary. But whenever we are teaching the machine an algorithm and the machine learns some particular data, what we mean by that is the machine comes up with a boundary equation. And then once that boundary equation is learned using the training data, then we say once the machine is learned, then the test data, it will say which side of the boundary it is, and then it will say that is the result of this. So this is fine, right? So now in this particular data, we have seen that if you draw a linear line, then we can easily distinguish between these two sets of data. But let's say if the data is like this. The data is like this. So you have dots and crosses and dots. So all of this is mixed together. So how will you find a decision boundary in this case? It's really difficult, right? Because everything is mixed together. It all looks the same, but you're telling me that they belong to two different classes, right? Because in this case, it's clearly separable. So you can either use k-means or you can use like any other algorithm to actually look at how to, like a linear algorithm, right? We can do a linear separator to distinguish. But if both of them are jumbled together, how do we deal with it? So that is what support vector machines will do. So the reason why support vector machines are so popular is because it knows how to handle, like in the training, if both the classes, when you plot them, all the observations are points, right? When you plot them into this space, you will see that if both of them are intermingled with each other, support vector machines will somehow come up with a boundary which is so complex. like maybe like this or like this, which is so complex that it can differentiate that. It does that some using something called as the kernel trick. We'll look at that what kernel trick is today. But support vector, the reason I'm saying support vector machines are so popular is because even though the data is intermingled or jumbled with each other, support vector machine can come up with a decision boundary for that particular data. Is that clear? Like why support vector machine is so popular, or like why it is used in, because if it's a simple case like this, like there are a lot of algorithms which can solve. But if it's a case which is as complicated as this one, then basically support vector machines are generally used for that. Is that clear? So I just told you like why support vector machine is important for us to learn, because it can so there's a law. So there's an algorithm called nonlinear SVM. Today we'll see how it can solve this problem. It's not very easy to like draw decision boundaries here. But before I do that, I want to introduce the concept of overfitting. So let's actually. So I want to actually, let me just clear everything. Anyone of you know what overfitting or underfitting is? Like, have you heard of it before? What is meant by overfitting the data? I'm assuming no one has heard about it, right? Okay, I'll tell you what overfitting is. You'll come across that term quite a bit in case of data science. So let's say, let me take that apples and oranges example. So we have apples and we have oranges. So we have like two class problem. One is apples and we have like a lot of observations. We have extracted features. So let's say oranges are represented here. And let's say apples are represented here. So you can clearly see that oranges are slightly on this side. So it's not a straight. So let me draw one straight line. Maybe some crosses here. So it's not a clear this thing, but let's say I draw one straight line, right? So this straight line is a decision boundary. It's a linear decision boundary. So in this case, what I'm saying is I just draw a straight line and I tell that this particular is my machine learning algorithm, which is basically dividing, it learned the data and it says anything beyond on this side is apples and anything on this side is oranges. This is what it learned. But is this thing actually true? Let's say there are some of them here and there's some of them. So it is not exactly true because you can see that there are some oranges on this side of the boundary and there are some apples on this side of the boundary, right? So this is just an approximation of learning. It works 90% of the time because most of the time, if you look at it, oranges are on this side and apples are on this side. But what if I come up with a very complex algorithm, which is like this? So I'll come up with another complicated algorithm, which is like this. Which is better? Or which one do you think is better? So this thing actually is exactly fitting the data. So it gets everything into the picture. Do you think this is better or the previous one, which was one line, is better? So, yeah. So this is one. The other one is like this. I don't know. So this second one is linear. And the first one is this complicated boundary. So is complicated boundary better or is linear one better? I think Satya said the complicated one is better. Anyone else who feels linear is better?
I mean, what are the x-axis and y-axis here? Like,
So
I mean,
x-axis and y-axis is like feature space, right? So this is
yeah.
feature one. Let's say two-dimensional feature, right? So I took two observations, so feature one and feature two, and then I'm just taking two features, so each one becomes a point. So there are like a lot of observations, but each one has two features. So I plotted this in the feature space. So
So
x-axis and y-axis are two features.
my question come in a kind of an answer is like, isn't it like if the variance is too high, complicated boundaries are better, and then if the variance is less, the linear is better?
That is one way to look at it. But here there is one thing you guys are. So I'll tell you what the answer is. The answer is linear is better because there is a concept in machine learning called as overfitting. So I'll talk about the problem a little in a little this thing. But so between these two boundaries, so I think Satya, you said like the complicated boundary is better, right?
Yeah,
Yeah. So you are absolutely right. The complicated boundary is better for because all you're looking here is the training data, right? So this is the training data. So yes, if you draw a complicated boundary, your training data is actually learned really well. So if you look at the complicated boundary, you have 100% classification. So in the training data, you are drawing the boundary such that 100% of the time when the training samples are on the other side of the boundary, either side of the boundary, they're classified correctly. But the main thing you have to understand is your evaluation of an algorithm is not based on training data, because in training data is only helping you to learn the decision boundary. Your main classification or your evaluation of the algorithm comes when you classify the test data. So you have the test data, right? So the reason why I say the linear boundary is better is because when you learn it too complicatedly, when your test data comes in, right? So sometimes the test data can come in here. Like let's say there's a cross here. Sometimes the test data can come in here. So the test data need not be 100% accurate, because in the real world, you have like more and more examples which can fall on this side. But just because you learn the training data so well and you define the boundary so well that you will get more test error. So your test accuracy may be only 90%. But whereas if you have your linear line, your test accuracy might be 92%. Is this thing clear as to why I'm saying this is the case? So sometimes it is okay to leave it in a general format because there is a lot of variance when you see the test data. Yes, you are absolutely right. This complicated boundary is 100% accurate for test training data. So when you take the training data, that is what is called overfitting. So when you're actually taking only the training data and you're defining this complicated boundary, 100% of the time you're absolutely right. It's going to classify it. But once the boundary is learned, this training data is irrelevant, right? So all it learns is this complicated boundary. But in the test data, there is so much variance that it need not always fall like this. It will fall. Some data will fall on both the sides of the line. So sometimes it is not good to overfit or overlearn the data. So an example for that is even like when you take a kid and you teach him too much, it only, I mean, or when you take a machine algorithm and you train them too much on only the training set, so you are overfitting the data for the training set. So it is not good to overfit because it will learn the boundary so complex that it doesn't have any wiggle room. So this linear boundary is still okay because even if there is some data which is falling on both the sides, your linear thing will take care. But if you overfit the data, that concept is called overfitting. So everyone understands what overfitting is. Overfitting is done on the training data. So that is the problem is when you learn the training data so well and then you create a complex boundary around your training data, that is called overfitting. And it is proven that because the test data has so much variance, it is not always good to overfit it towards one training data. There is something called as we'll see something in the next class called as early stopping and stuff, which will avoid this particular overfitting. But is this thing clear as to why I'm saying the second boundary is better? Because it's more generic, and we want to leave it at that generic point because you don't know how the test data would behave. The test data, it need not exactly behave like training data, right? So you shouldn't always overlearn or overfit the data. Is that clear? Any questions for overfitting?
So what if the test data is better for overfitting than the linear fitting?
Yeah, that's a good question. But so that is one such example. But if you take more and more examples, right? So it depends on, you're right. Let's say if the test data also behaves like the training data, then you're saying that this complicated boundary behaves well. But in 99% of real world problems, that won't be the case.
Okay.
Because training data is only like let's say for Google, right? If it's trying to classify words or something, it'll try to train it as much, but they don't overtrain it, because if they overtrain it, it'll learn it exactly according to training data. But in 99% of the problems, when the real world test data comes into picture, it's not exactly like training data. It behaves differently. You will see that when you write more and more algorithms. So there is this is what is called the bias variance trade-off. I'll talk about it in the next class because we have an entire lecture on bias variance trade-off. But 99% of the time, your test data and training data are not exactly similar. They are pretty much similar. That's why you're using the training data to learn the decision boundary. But you shouldn't overfit the data. So overfitting is the problem which actually increases the training accuracy to 100%, but your test accuracy falls. So that's why there is a concept in machine learning called, this is the number of iterations of your decision boundary. So your training error will go to 0. So this is error, y-axis is error, and this is the training error. But your test error will increase. So if you look at the graph, it will come down, but then it will increase later on, because at this particular point, you will start overfitting the data. So we will actually calculate, we actually will stop it at this particular point. So n is the number of iterations which is revising your decision boundary. So there is an optimal point at which you have to stop your iterations, because if you keep on overfitting it, your training error will go to 0, because it's learning it perfectly, but this is your test error. Test error will actually go down, and then it will start increasing, because you learn the data so well that your test will start giving you more errors. So I just wanted to introduce the concept of overfitting, because we'll use that in the support vector machine today. But is this clear? Any questions on this? So 2 main points to take away from this. What does it mean when we say a machine is learning the data? All it means is machine is coming up with a decision boundary. What is a decision boundary? A decision boundary is a boundary where on one side of the data, it belongs to one class. In another side of the data, it belongs to another class. So this is a simple 2-class problem, right? If there are 3 classes, let's say there is one more class, asterisk. Sorry, I'm not able to draw asterisks properly. So it'll create like another decision boundary. So today we'll use polynomial kernels, and we'll see how those decision boundaries are. But for now, let's just stick to simple 2-class problem. But everyone is clear what a machine learning model means. When a machine, we say, is learning, it means that it comes up with a decision boundary. And decision boundary means that if on 2 sides of the boundary, if the data falls on one side, it is one class. If the data falls on the other side, it's another class. So that's what is meant by a machine learning model. And then sometimes the models can be linear, sometimes it can be super complicated, but always ensure that you don't overlearn the data. You learn to an extent, like this is the graph, right? This one. You learn it to an extent where your test error goes down, but it shouldn't increase. You shouldn't overfit the data. So there is a particular sweet spot after which you should stop training. If you train it more and more with some particular rigidity, then it will basically create test errors in the later on. Is this thing clear? Questions on this? Anything you didn't understand here? I'm okay to explain it again. Raghav, any questions?
No, Sai. Yes.
So you understood what overfitting is and like why we should not overfit the data, right?
Yeah. Like I'm waiting for the next class actually when you said where you said that we should know where to stop.
Yeah, so that we will see. We will learn how to stop and how do we. So there are like a lot of things called cross validation and stuff. So next class we will look at that. But anyway, so this is something I wanted to introduce because we will learn that in this support vector machine lecture today. Okay, so, yeah.
Underfitting is the opposite.
I'm sorry. Underfitting is the opposite. Yes, you're right.
Too
That is,
general.
like very generic. It underfitting means that. It's exactly opposite of overfitting. So it's not even learned and like maybe like this. Sorry, this is an underfitting data. Like it's very generic, right? It didn't learn it even to an extent where it'll be able to classify it.
All right.
So underfitting is the opposite. So we'll talk about bias variance criteria, but like this is what is called overfitting of the problem. So overfitting is when you learn the training data so well that your test error will always remember that it's the test error is what we look after, because training is something we already know, but you want to evaluate an algorithm on the test data value. Anyway, so that is the concept of overfitting. So now let us look at the main thing which I wanted to tell you was, so I was telling like support vector machines are really good in classifying classes which are like this, right? So which are intermingled with each other. So how does support vector machine do this? So the algorithm which solves this is called nonlinear SVM. But before we learn about nonlinear SVM, let us look at simple math. Again, this is again a math-intensive algorithm. Don't panic if you don't understand the math behind it, because you don't need to know the math behind it, because the Python library will actually take care of the math behind this thing. So don't worry about that. So let me start with all right. So support vector machines. Support vector machine is a class of problems which is basically comes under supervised problem, and it is used for classification. So let us look at how support vector machine works. So let us take simple data which is like this. So again, from now on, by default, when I draw points, you have to understand that I've extracted features for an observation and I've plotted those features in an n-dimensional space where n is the number of features. So if I plot them in n-dimensional space, each of them becomes a point. So I'm assuming that I'm taking this for granted, that whenever you see these points and classes, please don't assume that it's only two features. You can assume it's only two feature set, but in general, it's an n-dimensional space where n is the number of features for every observation. So let's say we have a two-class classification problem. This is one class. Is everyone able to see my screen? The PowerPoint presentation?
Yeah.
You can see it, right? Okay. Let me present this actually. So we have two classes. In one class, when you plot this in the feature space, it is all green dots are here. In another case, all the red crosses are all here. So what we are doing in this case is basically, so ideally we want to create a line which separates both of them. Let's just consider this as linear problem. So remember I told you there is a linear problem where you actually can draw one line, and you can do a non-linear problem which is more complicated boundary. Let's stick to simple thing first. Let's see how support vector machine comes up with this particular line. So there is this line. So this is a linear problem. So how do you think this line should be? Like, let's say if I'm drawing this line which separates both the classes, what do you think are the properties of this line? Like, why only this line? Why can't I draw another line which is somewhat like this or like this? Like, why this line like this?
So basically, there's no relationship between the other two data sets.
That is one thing, but also this line is the one which actually separates both of them exactly such that the margin between both of them is highest. So if I can actually draw, so even this line separates it, right? So this is also a very good line, which for this particular problem, it separates it. But if you take the distance between this particular point and this line, and this particular point and this line, it's not maximum. So ideally, you need to come up with a line for which the margin between both of these things is maximum. So that's what is support vector machine becomes a mathematical problem right now. So of all the infinite lines I can draw in this particular plane, how do I come up with that one line for which this margin is maximum? So is everyone clear? Why should we draw this line? Which you can even draw this line, but then if you draw this line, it is the maximum, the distance is not maximum between both of them. So next time when you get a test data, which is maybe somewhat here, it'll classify it wrongly. The green dot is here, but whereas this one will classify it correctly. So how does support vector machine come up with, so this is linear support vector machine. We'll go into the non-linear one later on, but I want to start with linear one. So we need to always come up with a decision boundary for which the margin between both the classes is maximum. Is that clear?
No, Sai, like I'm just a little bit. So trying to understand this. These are three different data sets, right?
No, this is only two data sets. So this is one data set. Let's say this is class 1.
Okay.
And this is class 2. So class 1 is represented as green dots. Class 2 is represented as crosses.
So the linear line is nothing but the relationship what it shares between these two classes.
No. The linear line is not. Sorry, I think maybe that is. Where is this? 1 second. Just erase. So what I'm trying to get here is it's not the relationship between both. So I'm telling you that this is class 1, right?
Mm-hmm.
This is class 1. This is class 2. So I'm telling you that please come up with an algorithm which is linear in nature, which can differentiate these two classes very well. That means that I want you to come up with equation of a line, which is basically once you know this equation of this line here, let's say this is the equation of the line. So now we say that the machine has learned this line, so that in the future, if you get other points which are on one side of the machine, we'll classify them as class 1, or the other side of the machine, we classify them as class 2. So this is not, this line doesn't represent anything between them. I'm only telling you, like, I give you this data, this is all your training data. Please come up with a line which can differentiate between these two lines, these two classes the most.
So in our example, housing example, if you say the cost is higher than X, put it on the class 1, and if cost is less than a certain point, put it on class 2.
Yes, that's a feature, right? So like let's take the housing example, right? So this is cost, and maybe this is some other feature. Maybe this is square footage. So each one of them is one house, right? It's an observation. Like each of the point is a house, and there are two features, and we're plotting them in the 2-dimensional space. So all I'm saying is, so we are saying that this is one particular class of houses. This is another class of houses. So and this is your training data. I need you to come up with a decision boundary such that it can differentiate between these two data. Is there is that clear, or is there some confusion?
Yeah, I mean, on what basis we are trying to determine the decision boundaries, right?
The basis is basically the feature set, right? So now we are having two features, like one is cost and other is square footage, right?
Yeah.
So when I plot these particular points in this feature space, we are trying to differentiate them based on the gap between these two features. So this is one feature, this is another feature, right? So this is the 2-dimensional plane. I want to differentiate both the classes based on these two features. So when I plot them in this 2-dimensional space, right? So forget about it. I plot them like this, and this is how the data behaves. So this maybe all these classes, all these houses are higher cost, because you see higher cost, this is lower cost.
Yeah.
And if you look at it, square footage is pretty much similar. But what you want to differentiate that is based on the cost. But you need to draw a line, right, in this space to say that anything above this line is class 1, anything below this line is class 2. So all I'm trying to do is come up with a line which differentiates both of them based on where these points are located. Is that clear?
Yeah, so that line is an average cost. Is that what? Or
It's not an average cost. It could be. I mean, I mean, you can look at it like an average cost, but there, I will show you how the machine will come up with this particular line.
okay,
And this is so. This, I mean, don't go into how to solve it right now. How it solves it is it uses mathematical formula to solve it. But I just gave you this thing that if you have to, like, if I don't give you the machine mathematical equation, and I ask you that please draw a line which separates both these two sets, how will you draw it? So you can draw a line like this, you can draw another line like this, you can draw another line like this. But ideally the line which actually works to differentiate between both the classes is the line for which the margin between these two things is maximum, right? So when you so this line fits it really well because it actually has the maximum margin between both the classes. Is that clear?
yeah,
So I mean, this is what intuitively you would do, right? Because if I just plotted these points in that space and I tell you, please, you are the machine and come up with a decision boundary, you'll always come up with a boundary such that the margin between, these two classes is highest where this particular line can divide both of them. So how does the machine, how does support vector machine do it? How does support vector machine do it mathematically? So then what we can do is, let's look at a simple problem. Let's take 4 points. One is 0, 2, 0, 2, 0, 0, 0. So these two things belong to class 1. These 2 points, class 1. And these 2 points are class 2. So now, what do we do now? So basically, we need to come up, when we try to come up with a line, we'll try to come up with a line like this. So first one will pass through 1, 0, second one will pass through this. And this particular line will be the average of two. Actually, maybe you're intuitively right. It's kind of like an average between both those features. So you will come up with a line which is like this, which actually can divide it into two particular spaces. But then the way it'll try to do it is, let me show you this. So this is what is the mathematical equation for which you'll get the line. So there is some math here. The math is basically, I think again, this is high school geometry. The distance of what is the distance of a line from a given point? Does anyone remember, like from high school math? Basically, this is the equation for that. So again, if you don't recollect this, it's totally fine. So what we are trying to do is, we are trying to draw the distance of one particular point from, so let me draw this. So this is one particular distance, D1, and this is another particular distance, D2. So we want to actually maximize D2 minus D1, because this is the boundary between both of them, right? Or this is the distance between both of them. So we want to maximize the distance between D1 and D2. So if you take an example, so this is the equation of distance of any point from a line. But when this point becomes origin is x, y is 0, 0, right? Then it will become just this thing. So just bear with me with the math right now. We will. You need not understand how it is actually doing it, but what you need to understand is what it's trying to maximize. So given 2 points, given 2 classes, which is these two and these two belong to one class, these two belong to one class. The way the support vector machine comes up with a decision boundary is by looking at a line which maximizes the distance between this line passes through both the points,
this line passes through 1 point, right? So it'll try to maximize the distance between these two lines. And then this one is the average of both of them. So D1 minus D2 by 2 is what your actual decision boundary is. And the way it does it is by doing this math calculation. So it'll try to compute all possible lines, and it'll ultimately come up with a line for which the distance between the D1 and D2 is maximum. So if you look at here, so now there are two classes. You can actually come up with, so one thing, what is the equation of a line? Y equals mx plus b, right? Like in general, like whenever you have learned in high school. So you can always actually make the constant one by dividing the whatever that is. So generally equation of a line is like 3x plus 4y equals 5. Either you can write it like that, or you can divide it and say that 3 by 4, 3 by 5x plus 4 by 5 y equals 1. So we'll always write it in this form because we always want the equation to either be plus or minus 1. I'll tell you why in the next few slides. But is this thing clear, like what we are trying to do here? Given 2 points, we are trying to find out, so these are two classes. How do you find a line which divides both the classes with the maximum margin? For that, what we do is we basically take one. So when we are taking, so we take two parallel lines. First parallel line passes through maximum number of points in the second class. Because we can't, this one will not pass through this, but then it will find one other parallel line which passes through the second class. Then in these two parallel lines, we try to find the midpoint of both of them. So that is what is your decision boundary in this case. Any questions on this?
It's clear.
Okay, so let's. So this is just explaining vocally, but then let's look at how the math behind this works. So basically, the math behind this is what they do is, what algorithm does, it takes a point, generally the origin, and tries to draw the distance between origin to this point and distance between origin to the next point. And then it just subtracts D2 minus D1 and tries to maximize that distance. So if you look at it, so this is what is the equation we'll try to find. So there are two classes. One is the red class and the green class. And then it will try to draw one hyperplane such that the distance between both, like this hyperplane actually divides both these classes equally. So there's a D plus and D minus. So for that, what they'll do, what it tries to do is it tries to find an equation of a line. So this is expressed as W dot X minus B equals 1. So how did they get this thing? So W is basically the vector. So let us actually write the equation of a line. AX plus BY equals C. Step number 1, you normalize it. A by C plus B by Y equals 1. So when you say X here, it is the point X and Y. So this is basically nothing but a vector, A divided by C and B divided by C, multiplied by X and Y equals 1. Or you can actually get, let me just erase this. So you can actually get a point plus minus B equals 1. So you can actually take a constant here, which is basically the bias between, so this B is such that these two are divided equally. So this becomes your WX plus B equals 1 and WX minus B equals 1. So don't worry about if you don't understand how this line comes. All you need to know is it's trying to actually create a distance between both of them such that you can actually have a hyperplane which is dividing between both of them together. So if you see, what it's trying to do is define a hyperplane H such that X, mind you, this X here stands for X1 and Y1. So Xi here means X and Y. And W is the weights, A by C and B by C. So what it tries to do is it tries to actually give you a label. So the Wx plus B is greater than plus 1 when Y is plus 1. Wx plus B is greater than minus 1 when Y is minus 1. What that means is, if you try to find these two equations of lines for which this is +1 and this is -1, all the points on this side of the line, it'll have a value which is greater than -1. All the points on this side of the line will have values which are greater than +1. Is this clear? This is how it'll try to define them. This is what is happening behind the scenes of what SVM does. So ideally, why we are doing it is because if it is greater than +1, -1, we are saying that greater than +1 is one class, less than -1 is another class. So it'll try to define two hyperplanes such that for the first one, this is +1. For the second one, this is -1. All the points beyond this particular point, you will get values which are less than -1, and all the points which are greater than this point, you will get values which are greater than +1. So the margin is the hyperplane separating this d plus and d minus. So let's look at the next. Is this confusing, or is everyone following the math behind this?
Actually, it's easier along with the math.
Okay. What if between -1 and +1? Sorry, I didn't get, Meher, I didn't get your question. What if between -1 and +1? Oh, what if it is between -1 and +1? Oh, that's a good question. So the way it is trying to define it is basically, let me go back to that slide. So his question was, what if it is between +1 and -1? So the reason, you won't have any points between +1 and -1, because the way you're defining this particular line itself is by saying that the ones which are, okay, so let me go back to this example here. So you won't have any points between +1 and -1 because you're actually drawing the first line such that the first point of the first class, the closest point of the first class lies on this particular line, and the closest point of the next class lies on this particular line. There are no points in between both of them. So that's why you won't have anything between +1 and -1. So you are actually taking the line and then saying that I want to define this particular line such that it becomes +1, and the other line is such that it becomes -1. Everything else is manipulated accordingly. The equations of ax and by, so ideally ax plus by plus c equals 0, is actually manipulated such that you get, for this equation you get -1. For this equation you get +1, and for this equation you get -1. Is that clear? So there won't be any points in the training data for which. So if there is anything else here, this particular line will be moved there. So you always organize these two things such that this boundary will have +1 and this boundary will have -1. The reason we do that is because this is what we want to optimize the equation as. So the equation becomes, the margin between both of them becomes 2 divided by modulus of W. How do we get that? Is because when you substitute, if you again go back to the equation of a line, right? This thing, distance of a point from a line, if you substitute the origin, and then since C here is +1, right? For one case, and C is -1 the other case. So when you take D2 minus D1, you will get 1 divided by mod of this thing minus of -1 divided by mod of this thing. So ultimately it will become 2 divided by mod of this. That's how you get this 2 divided by this thing. Is that clear? You won't have any point because you are defining the line itself such that the first point which you encounter in the second class is this particular hyperplane, and the first point you encounter in the in class 1 is this particular hyperplane. So that's why you are defining, and the line which is dividing both of them is going to be the average between both of them, which is this thing. So all you're trying to do in this case is try to come up with a decision boundary such that these two classes can be separated the maximum distance. Even if, again, let me tell you, even if you're not following how you're getting this thing, don't worry about it. I'm just trying to explain it with the math equation so that in case if you want to dig further and understand how this is being done, it will be helpful for you in the future. But all you need to know is support vector machine is always trying to, so this is a linear support vector machine. So it's called linear SVM. So linear SVM always tries to come up with a line such that the line has maximum distance between class 1 and class 2. Is that clear? And the way you actually get that is by saying the distance of the origin to that point. So if you go back here, since I've defined my line as +1 here and -1 here, the distance of origin to this particular line and distance of origin to this particular line, this is D2 and this is D1. And this one will be D2 minus D1. So that is nothing but 1 of -1 divided by mod W. So this support vector machine is still drawing a line between two distinct groups, and how would it do it when it's jumbled? So don't go into the jumbled part yet. So I'm going to like that. So I took a simple case right now. So right now I'm not looking at the jumbled case. So that's a good question. That we will see when we do nonlinear SVM. So for now I'm just starting with simple SVM. So I'll actually make you understand the math behind it, and then we will try to do it when it's jumbled. So for now I'm not considering the jumbled part of it. I'm only doing the linearly separable part. Is that clear? All right, so let me go further with this. So it becomes, again, this becomes a slightly mathematical problem right here. Okay. So the problem is so we have seen that in this case, so we've seen that the problem becomes like we need to find a value such that this 2 divided by mod is maximum. So that is the distance between both the lines. So the equation then becomes, we need to find W and B such that this distance is maximized for all the points. Now, tell me, if 2 divided by W is maximized, then is it the same as W is minimized? Because 2 divided by something is maximized means that W is minimized, right? So this can be formulated as this mod of W is minimized for all the points, such that Y minus, so your label here, this is the label, right? So if this value is negative, your label is also negative, so Y times W times Wx plus B will always be greater than 1, because for the labels for all the points here will be something less than negative, like less than -1. Labels for everything above this particular line will be greater than +1. So when you multiply the label times this equation of the line, they all will be greater than 1. So this becomes the constraint equation for solving the support vector machine. So the problem becomes, you need to minimize this particular value such that for all the points, Y times W transpose X plus B is greater than 1. So this is how support vector machine will find out this line. So I'll just take a minute here to actually make you understand if there are any questions over here. So this is like, again, like, so don't worry if you don't follow what like the math behind it. I'm just doing this so that it will be helpful for you in case if you want to understand in the future. All you need to know is somehow the support vector machine has to come up. And how does it come up with it? It comes up with this particular math. It tries to draw 2 lines, one for each class. So class 1, it will have 1 line here. Class 2, it will have another line here. It will try to maximize this distance between these 2 lines such that the middle line is actually the one which differentiates both the classes the best. So support vector machine, the main job of support vector machine is to come up with the equation of a line such that it can distinguish between both class 1 and class 2 to the maximum extent. Is that clear? So this becomes the equation of the line. So don't worry if you're not able to follow it to an extent where this is there, and this will be there for your reference, because if you actually go study any chapters on support vector machines, they'll come up with all these. So I want to introduce the basic math.
So, sorry, quick question here. Sorry
Yeah.
to interrupt you. So, support vector is always parallel to the other two classes, right?
Yes, that is correct. These two lines are always parallel to both the classes, such that that's the reason you get this 2, right? Because you're subtracting 1 and minus of minus 1. So these two are parallel lines. So that's when you actually, so at the end of the day, it uses this equation to find this line. So if you're using the support vector machine package, it will directly give you that equation of the line. So you need not worry how it is doing. I'm just showing you how it will do. So the problem becomes this thing. So from this point on, the math is going to get slightly more complicated. Don't worry. So for people who are interested in math, because like how the algorithm is created is completely based on math. So if you are not following the next few slides, it's completely okay. As long as you understand that linear support vector machine tries to draw a line such that it maximizes the distance between both the classes. And then I will talk about if the data is jumbled, how it will do it. So the next few slides are just for informational purposes. And I think it will be useful for college students because they might be using the math in the future. I'm not sure. But if at all you are not following it, it's totally fine. So let me just go ahead and I'll talk about some math optimizations and stuff like that. So when you are given a condition such that you need to minimize this particular thing, given certain conditions, it actually falls under something called as Lagrange conditions. So Lagrange conditions actually are helpful when you're trying to minimize something given some conditions like this. So what this mathematician Lagrange came up with, he says that if at all there is a function and there are some conditions, you can actually take that condition into your function itself by adding something called as support vectors. So now I need to minimize this such that this condition is maximized, right? Such that this condition is met. So what he says is W transpose W plus some alpha times Y, so this equation. So Y times W transpose X plus B minus 1 equals 0. So that's what Lagrange says. Whenever you want to solve a function which has some constraints, you can take those constraints and create a new equation, which is like this. So don't worry if you don't follow this, it's totally fine. I just want to show you how I got from this optimization problem. There is a reason I'm doing this, because I want to introduce to you kernel product and kernel functions. That is the main thing in support vector machines. And to understand that, that's why I'm teaching you this math. It's not just to confuse you or something, because that will be really helpful when you go to this nonlinear or jumbled data space to understand how that is being done. So first thing is basically given, so did you guys understand why or how did we get this? We got this because we said that the way we created these two lines are such that any point which is beyond this line will be greater than plus 1. Any point which will be less than this will be minus 1, right? So if I take that particular label and multiply it with this equation, both negative times negative will become positive. Positive times positive will become positive. So that's how you get this condition. But if it is, if you're not following it, it's fine. Go through it leisurely if you afterwards, because I'm recording the lecture. But the main thing you need to understand is support vector machine comes up with this particular line using this optimization equation. The optimization equation is 2 divided by this has to be maximized for all these conditions. So if 2 by this is maximized, that means this has to be minimized, right? Because 2 by x, if it is maximum, that means x has to be minimum. So it just transforms that into W transpose this thing has to be minimum with all these conditions. And the way you solve this is basically using Lagrange multiplier. So I don't know if you remember linear algebra. So how do you solve for some maximum and minimum? Let's say you have a function f of y. like AY plus C plus D. So you actually differentiate that, right, with Y and equate it to 0. So this is linear algebra. So if you want to maximize a certain function, you differentiate that with that particular variable and equate it to 0. So the only reason Lagrange multiplier is useful is because if you have a condition, you incorporate that condition into your equation using Lagrange multiplier. So you just add that particular condition into your original condition, and then you do a differentiation of that equation. So if you actually differentiate that, let me look at this thing. So you are trying to solve this problem where you want to maximize W transpose times W, and you want to add Lagrange multipliers to it. So I won't go into this Kern-Tucker conditions and all. So the Kern-Tucker condition says that this particular problem will have a solution if these things are met. So, and the design is common. So don't worry about this thing. So the main thing which I want to show you here is once you have these conditions, so ultimately this is what you're trying to maximize. So when you actually incorporate that condition into your W transpose times W, you will actually get this particular equation for you to optimize. So how do you optimize this? You actually take a differential of that with each respect to each value, W, alpha, and stuff like that. So, okay. So when you optimize this equation, so what this tells you is all the other points which are not part of this parallel lines, for that the Lagrange multiplier becomes 0. Because ideally you don't need them, right? You're just taking one parallel line which passes through these 2 points and another parallel line which passes through this point. So alpha is this Lagrange, so let me go up here. So alpha is this Lagrange multiplier which you are adding to that equation. So this is alpha. You mentioned it as wavelength, this thing, but this is alpha. So what it says is when you solve this particular equation, you basically only require those particular points from which the parallel line passes. Rest all of the points are useless because the line equation doesn't depend on them. And when you solve it, you'll understand that all the alphas are 0 for points which are not passing through that parallel line, and alphas are non-zero for which the lines are passing through this parallel line. So that's what he says. Like when you actually solve for them, the values for which alphas are greater than 0 are called support vectors, and for which they are non-zero are called are useless for us. So you see the support vectors are only these 3 points, 1, 2, and 3, this and this. So why are they called support vectors again? The whole algorithm is called support vector machine, right? Support vector machine means that you actually have 2 points, like these are the 2 support vectors for this parallel line. This is another support vector for this line. So you actually try to come up with the line which is passing between both of them. So let me actually stop at this particular point before I go further. So forget about the math, but how many of you understood what we are trying to do here? Like how we are getting that equation is irrelevant if you're not following the math behind it. But all we are trying to do is, of all the lines which can separate these 2 classes into 2 of them, we are trying to find that particular line for which the distance is maximum between both these points. And how we are doing it is using Lagrange multiplier. Is that clear?
Yeah.
Yeah.
Okay.
So coming back to our solutioning, right? So this activity we do generally to come out with the accurate test data.
This activity we do is to come up with a line which has the maximum margin between both the training classes. So again, if I go back to this, right, this is class 1, or this is like, for example, in Indian labor, or let's say housing example. So this is one class where the property prices are really high. This is another class where the property prices are really low, or vice versa. How will you come up with that one line which differentiates between both of them such that there's a maximum distance between both of them? So how do the way it is actually coming up with that line is what the math is talking about. But ultimately, what you need to do, what you need to remember is, given some linearly separable data, support vector machine uses these support vectors to come up with this decision boundary, which is actually the best decision boundary to differentiate between both the classes. That's the takeaway from this. Is that clear? So all it's trying to do is coming up with one line which separates both of them, and the way it is doing it is by using this. So I'll go a little further, because the reason I want to actually talk about this is so support vector machine is probably one of the most complex algorithms. So I will split it into two classes. So I'll just do linear support vector machine in this class, and the jumbled data I'm going to do next class, because I don't want to like cram everything into one class. So remember when I told you, like, mainly reason we use support vector machine is when we have the data which is not linearly separable, and then it actually somehow comes up with a complicated decision boundary. That we will do in next class. But the reason I wanted to show you this is because there's something called as kernel functions. So if you understand or not, just bear with me till the next few slides. Then if you don't understand, we will then see how to solve it. So basically, so using the Kern-Tucker conditions, we've actually included that value into, so we have included that particular value of like that yi times, ax plus b greater than 1. So what he says is, like, if you use alpha, and you can just get this condition into your original equation, ax plus b minus 1. So you just got that condition into your original equation which you're trying to maximize. And then he says, when you solve for this, you will see that the alphas or the support vectors will be only positive for the lines for which the parallel lines pass through. That means that these all data is useless, right? Because there's no line passing through it. What it does is it tries to start from one line and tries to expand like this. And then first parallel line which you get for the first class is here, and another parallel line you get for the second class is here. And this is passing through one point here. This is the called support vector, and you get non-zero values for this thing. And the rest of them are all zero values. So you need not worry about that. So basically, so this is a simple differentiation math, like how you calculate the maximum of a particular line, right? You just take and then differentiate it with that particular variable. So once you differentiate that particular variable and equate to 0, you will see that. So this is the main thing which I was trying to get at. So you will see that when you try to optimize that particular line, you will see that each of them, the optimal result is a dot product between both the observations. So xi transpose times xj is nothing but the dot product of xi times xj. Why is this important? I'll tell about this in next, I'll tell in the next few slides. But when you try to differentiate and try to find that equation, just remember that the result depends on the dot product of each of the observation. So when you can, if you are interested, you can go through this math in detail, but then just understand that the dot product between with all the observations is what the optimal equation depends on. So this is what is called the dual problem. But ultimately, when you try to solve this, all it's saying is the dot product of both the observations is what it depends on. And the reason why this dot product is important is because when we learn kernel functions, you will understand why this dot product is important. So let me go further. So it depends in the form of the dot product. So once you get the optimal, so what are we trying to find here? We're trying to find the values of W and B such that this equation is satisfied. So that's why you differentiate that with W and you differentiate that with B and equate it to 0. And once you equate it to 0, you will get this as your optimal function, where it depends only on the dot product of this thing. Okay. So, okay, even if you didn't follow that, it's totally fine. The reason I only thing you remember is when you're trying to solve it, it depends on the dot product of this thing, dot product of the observations. So x transpose xi transpose times xj. It depends on the dot product of both of them. So remember that, and the reason for that is because I'll talk about kernel functions now. So let's go into this thing. So okay, now we understood, like if it is linearly separable, we can come up with a line, right? So if the data is like this, we can come up with a line like this using the equations we have seen above, which will differentiate these two classes into perfectly with a certain margin, right? Then that's what the equation actually told you. But then how will you do it for this? Let's say if the data is like this. Obviously you can't draw a line, right? Any line you draw, like, okay, if I draw this line, I have some points on this side. If I draw this line, I have some points on this side. So it is not possible to actually come up with a line. So this is the case of the jumbled data. So what nonlinear SVM does is it tries to project this data into some other dimensional plane. So it basically takes this data and comes up with another higher dimensional plane. So you actually try to project it another dimension, such that in this new dimension, this data becomes linearly separable. Is this clear? So if at all the data is not jumbled, then we can draw a straight line. But if the data is jumbled, it actually projects that particular points into a higher dimensional plane, such that this particular plane, in this particular new higher dimensional plane, this data is linearly separable. And then it uses the same optimization equations which we have seen here to find that. So if the data is like this, we saw that we can come up with a line using optimizing certain lines over here, so certain parameters here, to come up with this line. But if the data is jumbled, then there's no way you can come up with a linear line. So what it will do is it will try to take this particular point. Let's say we have 10 feature space, right? So we have like feature 1, feature 2, x is each feature space up to feature 10. It will project that into, let's say, maybe 20 feature sets. So it will take this and come up with some new features, F1 to F20, such that in this particular new dimensional plane, this data is separable. So you can take, so from a non-linear separable data, it will transform it into another dimension plane such that the data becomes linearly separable. Is that clear? That's how it solves this problem of jumbled or mixed up data. Any questions on this?
It makes sense.
So what it does, so original space can be mapped to some higher dimensional feature space where the training data is separable. So that's what it does. Again, how do you solve? The reason I told you this Kern-Tucker conditions and this thing is because I told you that this is basically the dot product, right? The beauty of this equation is that you need not know what this new space is when you're trying to solve it. So that's why I actually introduced that equation. So let's say, okay, so let's say, let me take this example here. I'll show you that later, but I have an example where you will understand this better. So this is the case. So let's say you have 2 points, x1 and y1, and then they are all jumbled up, right? So you're transforming. So what you're trying to do is I'm taking this and I'm transforming it into a new space. So this is that new space. So how will someone guess what this new space is? Like, okay, I have 2 features set. In what space should I transform this particular 2 points such that it becomes linearly separable? It's very hard, right? Like I have 2 features. Let's say I have the cost of the house, and then let's say I have square footage of the house. So these 2 things are something I know. But if I take these 2 features and then I'm saying I'll transform it such that I get 4 or 5 features, I don't know how to get that. Like what linear combination should I actually use on these 2 features to get this thing? It looks very complicated. This is a new feature set. So what this So that's called the kernel trick. I'll talk about that later. So what this does is, when you're trying to solve the problem, you need not know what the new space is as long as you apply a kernel function. So I will just bear with me for like next 10-15 minutes, and then we will see why it is not important. So for the two takeaways: if it is linearly separable, using this optimization equation, it comes up with this line. But if it is not linearly separable, there is an additional feature space where you can project these points into that space such that in this space it becomes linearly separable. And that's how the support vector machine actually works. So then when you get the test data comes, it'll project it into the same space. And because in this space it has learned the linear separability, right? And it'll say that on whichever side the test data lies, it's going to classify it like that. So it won't classify it in this particular plane because it's all jumbled. It takes this plane, computes a new dimension space, and projects it there, and it computes it there. So that's why support vector machines is so powerful, because even if your data is jumbled in this space, it'll come up with a new dimensional space where the data can be linearly separable. And how do we come up with that space is what I'm going to talk in the next 5 minutes. What's the time? Oh, we have time. Okay. Is it, is everyone following what is happening, or? Okay, so Satvik asked, when it's transformed to the new feature space, does it still separate it linearly? Yes, it transforms it into the linear space where it is separated linearly. So it doesn't, so it's not like it is coming up with this transformation randomly. The transformation it does is such that the data is linearly separable. So if it cannot be linearly separable, then it doesn't do the transformation. So it's not like a random transformation where it'll try to transform and then it'll become linearly separable. It is transform, it's the other way around. It transforms it into that space where this data becomes linearly separable. I think Satvik was asking a question: what happens if even after transformation, if it's not linearly separable? So it will be linearly separable in that new space, and how it comes up with that is the next few slides. So what it is, so all it, one second, before we do hard margin. So all it does is basically in this new space. So, okay. So it takes X and comes up with a transformation function, right? This is what I'm telling you. It takes X. Maybe if X is like X1 and X2, the new space will be a combination of these two things. Like it'll have like 4 or 5 dimensions where it's X1, X2, or X1 root, X square root of X1, square root of X2, or some kind of a transformation it does such that this becomes linearly separable. And then the way you optimize that equation is exactly the same as this. But do you see that, or maybe I'll still ask this question. So once we actually did this equation, right, I told you it depends on the dot product of these two of each individual vector. Now assume that if I'm transforming X to like some other new space of X, and like both of them are transformed to this new space. So when you optimize that equation, what would it depend on? What would the optimal equation of the new space depend on? Like, because all I'm doing is I'm just transforming it into new space. I'm still using the same equations, because once it goes into this new space, it still is the same equation as what we have here, right? Because here I'm looking in 2-dimensional data, but that is like a higher dimensional data. So this is what is called the kernel trick. Before I go into soft margin, half margin, this thing. So linear classifiers in higher dimension space. So initially this one is basically not separable properly. So you define a function such that you map it into a different space such that it's linearly separable in that space. If you do the same Kern-Tucker conditions and Lagrange multiplier for this, you will see that the resultant of that is also the dot product of that new space. Because it's the same equations, right? instead of having x, we are now having x phi of x. So if you solve this particular equation, still the same original formulation, but instead of x, we will have this new feature space x. But the thing which I'm trying to tell you guys from that particular point of time is the optimal equation depends only on the dot product of the equation. So I don't need to know what the individual function is, but I just need to know what the dot product of both of them is. So it's this is what is called the kernel trick. It's some people ask you this question quite a bit if you are like. So I think it's a little theoretical, but it's good to understand what kernel trick is, because you'll be seeing it used in a lot of places. The kernel trick means that because the optimal equation just depends on the dot product of these two things, the kernel trick says that when you take so if you actually find a transformation such that this particular kernel can be expressed as a dot product of two individual higher dimensional points, then that particular thing is linearly separable. So this is what is a kernel function. So what I was remember I was telling you that you don't need to know what that new dimensional space is. So let's see what I mean by that. So let's say if the space is this and this is the kernel function. Kernel function means that the kernel function is the dot product of the new space. So let's say if this is my vector x1 and x2, and the new space kernel product is, I just choose this, right? 1 plus x1 transpose times x2. Then if I can express, so what I've done here is I've actually taken this, expanded it, and I've expressed the same thing as a dot product of two particular points. So this thing, this particular expansion is expressed as a dot product of two particular points. So if this can be expressed as a dot product of two particular points, then the kernel trick says that there exists a space in that higher dimension where this is linearly separable. So you need not know what the transformation is as long as you know what the dot product of that particular new space is. So this is what is called the kernel trick. This is maybe a little difficult to understand, but let me show you how this translates into the code. So let us open this. So if you actually see, so support vector machine, though you learned so much theory, the code part is just 3 lines. So all it does is it takes this thing. So if you see the support vector machine, it has this function which takes these 3 parameters. It's called what is the kernel, what is the soft margin, what is gamma. I'll tell you what soft margin and gamma is, but you pass in something called as the kernel. The kernel can be linear, it can be an RBF kernel, it can be any other kernel. All this kernel does is it transforms the current dimensions using this particular kernel function into a higher dimension space. And what is this kernel function? The kernel function is nothing but the dot product of those two vectors. So that's all it means. So I can choose this as a kernel function. Not all functions are kernel functions because it has to satisfy those conditions where it can be expressed as a dot product of two of those higher dimensional points. Let me see someone asking some questions. So, okay, there's some questions here. Can every data point be separable? Are there cases where it cannot find? Yes, there are cases where you cannot find a higher dimension space where it's linearly separable. So it is only possible in the case where this kernel trick is actually justified. So these are the conditions it needs to satisfy. It's called the Mercer condition. I don't want to get into all those details, but not all kernel functions can transform it into a linearly separable space. So there might be spaces where it cannot be linearly separable, or there might be cases when this particular data, when transformed into higher dimension, is not linearly separable also. So this kernel function works so you need to try out different kernel functions. That's why I was actually talking about this. So there's one kernel called linear kernel. There's another kernel called RBF kernel. So when you look at, I actually did there's a polynomial kernel, there's an RBF kernel. If you look at svm.svc documentation, so all of you, when you're doing these things, look at the documentation from sklearn as well. So in the documentation, if you see, there are different kernels which you need to put. So the kernel, what the kernel does is it takes the non-linearly separable data, applies that kernel function, and puts it into this new dimension space where it will try to make it linearly separable. So it's a hit and trial error. It's a hit and trial thing. It is not 100% that it's not 100% that it will be linearly separable. So there's one more question. So the kernel trick, only if there is a space where it can be linear, it doesn't tell which space. Is that right? The kernel trick doesn't. Yes, that is correct. So the kernel trick is used if there exists a space where it is linearly separable. It does not tell you what that it does not tell you what that space is, because it is only seen as a dot product of these two things. You can take the dot product and divide that into two dot products, so you'll know what the space is. So if you see this example which I'm showing here, so I have taken this as the kernel. So this is my original space, x1, x2. I'm saying I want a new space where the kernel thing I'm applying is 1 plus x1 times x2 squared. So if you want to know what the new space it's projecting it, because this is the dot product, right? Expand this and express it in terms of dot product of two vectors. So when you express this as a dot product of those two vectors, that means that x1 and x2 is basically transformed into, this is new space is 1, x1 squared is another feature, square root of x1, x2 is another feature, x2 squared, square root of 2 times x1. And so this is what is the new space, but you need not know what that space is, because the output is the resultant optimization is the dot product of both of them. So if you actually just take this as the kernel function, you'll be good enough. You need not know what exclusive transformation is required. All you need to know is what that kernel function is. So that's why the kernel product, or the kernel product is that's what the kernel functions are important. So the reason I told you all this is because your SVM takes the data and takes these three parameters. I mean, these are some of the parameters which you will change in your exercises. First thing is the kernel function. The reason why we are using kernel functions is the kernel function is what tells that you need to transform it into a higher dimensional space where this data is linearly separable, and you can use your test data there. So you can use different kernel functions. So this is one kernel function, right? One I have used here is one kernel function. There are RBF kernels, there are linear kernels, there are polynomial kernels, there are a lot of other kernels, so which are part of the SVM library. But you need to understand what this kernel is. All the kernel is doing is basically transforming the data which is not linearly separable in the current feature set into a new dimension space where it is linearly separable. Is that clear? I'll take so this is all about SVM is just that. So nonlinear SVM takes the current space. If it's not linearly separable, it will project it into a new space and make it linear. And how it does this projection is got by this kernel function. And kernel function is nothing but the dot product of this new dimension space. The reason you don't need to know what the explicit transformation is because you won't use that explicit transformation anywhere. You'll only use the dot product of that. Because if you have seen that when we solve those equations, we only use the dot product of those two vectors. We didn't use the exclusive transformation as such. So as long as you know what the dot product of those two vectors are, you're good. So that's all it does. Yeah, it does. So basically, there are some disadvantages of SVM. If the number of features are greater than the number of samples, you might overfit using the kernel function. So that's what I mentioned, right? So there is something called as overfitting. If you don't choose the right kernel functions, you might overfit the data. And the other thing, so yeah, sorry, I have to tell you what this C and gamma are. Let me explain to you what C is now, and then gamma will do next time. So Is this thing clear? Like we are passing kernel functions into support vector machine. All this theory, all the thing which I was talking about was only for this particular thing. Like what does this mean? Why? What does the kernel mean? How are we calculating the kernel? And what is the kernel actually doing? The kernel is actually projecting this space into a higher dimensional space such that the data is linearly separable there. All it does is just that. Is this clear, or any questions on this?
Questions?
It's clear, Sai.
Okay. So all we need to know from all that math is basically what kernels are. Not everything is a kernel function. Only kernels which can be expressed as dot products of those two higher dimensional spaces is what kernel functions are. You need not go into like the whole thing of like, oh, what will be happen if it doesn't meet the Mercer conditions and all. Don't worry about all that. This will take care. This particular equation. So this is like really simple code for support vector machines. So all it does is you just need to take the data. I'll explain. I'll walk you through this code if we have time, or else we'll do it in the next class. But main thing which your support vector machine takes is basically this kernel function, which can be a polynomial kernel, RBF kernel, linear kernel, a lot of kernels, and all the kernel function needs to satisfy is this particular criteria. The criteria being the kernel product has to be expressed as a dot product of two vectors, and it should meet this Mercer condition example. So when it meets the Mercer condition example, then we say that the kernel is positive semi-definite, and that's a criteria for transformation. Anyway, so this is what is the kernel which we pass through it. So basically, if the data is jumbled up, then support vector machine uses something called as the kernel trick or a kernel function to transform it into some higher dimensional space, which you need not know, because all you need to know is the kernel, which is the dot product of that space. And once you transform it there, you can linearly separate it. So now let's see what does the C mean. So now this brings me to this particular question. So let us actually take this example here. So in this example, I have some data which is basically, there are some points here which belong to the first class. And there are some points here which belongs to second class. But you can see that there is one point which belongs to the first class and another point here which belongs to second class. Now tell me, how do you actually, which one is a better classifier? Is this a better classifier, or this is so this is 1, this is 2. If you have data like this, what do you think is a better line to divide both of them? Is it 1 or is it 2?
1.
Why not 2?
Because the margins are too low to determine, like
Yes.
from the.
So you're exactly right. So 1 is the better classifier. But the reason why we are not, if we use the same old linear classifier, we won't get 1, because remember I told you we first draw these parallel lines. So the first parallel line is here. It will stop as soon as it hits this parallel line. It won't go till there, because we saw that these points are irrelevant. First parallel line it gets, once it hits the second class, it'll stop there. It'll try to form a line which is here. So that's why they have something called as soft margin and hard margin classifiers. So what that means is, you're right, this is a better classifier because this has much more margin between them. But there are some points of this class which are here, then there's some points of the other class which are here. So what they said is, so now what we'll do is, instead of solving the equation which we solved earlier, we will add something called as a penalty term. So the penalty term EI is going to be taken into our equation again. So for every point which is misclassified, because if we draw a line which is here, this is misclassified, right? This point is misclassified because this belongs to class 1, but
but we are saying that, hey, this belongs to class 1, whereas it's class 2. So what the new hard margin and soft margin says is, for every point which is misclassified using this particular support vector, we'll add an error term. So apart from having the original ones, they added an error term to the equation. Original equation was only this, right? This plus this. So they added something called as an error term for this classification. So for every point you misclassify, you give a small error term to it. And the weight for that error term is what is C. So higher the C, that means the higher the hard margin classifier. So so this is the example. So for this, if you want a higher, if you give a higher weight for every misclassification, it will become hard margin. Hard margin meaning it has to be exactly true to actually make it to to actually get the divider. Soft margin means that if C value is like less, like 10 is less and C value is 100. So that means that you're penalizing every misclassified point by 100 times. So your margin becomes closer and closer to the first class. But if you give less weight, if you say, okay, no problem, only 10 is your error margin, then it will become like this. So that's what the C is here. So if you actually look at the code, there are 3 things I said, right? So one is the kernel. So this is polynomial kernel. That's why the degree is there. But let me take a simple linear kernel. So if you take a simple linear kernel, this C is what is, in this case, C is 1. That means it's a soft margin classifier. If I make C 100, then it means that the classifier is very, very strict or very, very rigid, like in this case here. So it becomes like this. So in general, for handling problems which are like this, we use something called as C. If you lesser the value of C, the softer it is on the data. The higher the value of C, the stricter. That's why it's called soft margin and higher margin. Is this clear? So all it does is basically, if C tends to infinity, then we get closest to hardest margin. Soft margin will have a solution and it's more robust to outliers. This is an outlier, right? So that's why we use the value C. So C trades off the margin width and misclassifications. So instead of optimizing only W, we actually add errors and with the weight C, and we actually optimize that. So this is what a soft margin and hard margin does. So mind you, in all our lectures, this is the most complicated algorithm. None of the algorithms are this complex. So if we clear or if we understand this, rest of them are very, very simple when we take neural networks or this thing. But support vector machines, it is complex to understand because of this thing. But I hope like the math and everything is sufficient for you to understand what kernel trick is, or what RBF kernels are, or what kernel functions are. So kernel function is nothing but the dot product of the newer dimension space, which we pass to the SVM function, such that this becomes it becomes linearly separable in that new space. And the higher the the higher the C value, the harder or the stricter is the boundary. The lesser the C value is less strict is the boundary. So basically this is the thing. So there is another thing called gamma. Gamma actually is the overfitting. So if you actually have higher gamma, that means it is it doesn't fit well. I mean, you avoid overfitting. Sorry, higher the gamma, lesser is the overfitting. Lower the gamma, higher is the overfitting. So basically that. So this is another parameter which you can change using SVM for looking at like overfitting and underfitting cases. So we have some more questions on the chat. The degree is an option. The degree is only for polynomial. Yes, that's correct. Because degree, if you want to fit a polynomial kernel, basically that's when you use degree. It's an optional parameter. So when should we use C? So when should we pick C, which is lower or stricter? So this is a very good question. So you actually choose C for. So remember, I spent a lot of time in data visualization. Now that's the reason I spent a lot of time in data visualization, because once you visualize the data and you see that the data is jumbled or garbled, then you go for kernel functions. and then you see when you actually see that the data even after projecting it to higher them, or if you take linear kernel function, right, in which there's no projection done, and you see that the data is somewhat like this, that means you have outliers, then you use softer C. So if you take a lower value of C, then you'll get this thing. But if you take a higher value of C here, it becomes very strict. So the things which will help you decide this is once you do data visualization. So once you visualize the data, when you plot the features here and you visualize the data and you see that there are outliers, then you use a lower value of C. But if there are lesser values, if there are no outliers, then you can give a higher value of C. Does that answer your question, Meher? Sure. So I will actually give you an exercise in which you will change the values of C and you will see different results for different things. So gamma for now, don't focus on it because I'm going to teach bias variance trade-off in the next class. So gamma actually represents that, like, higher the gamma, less is the overfitting, and lower the gamma, higher is the overfitting. So leave the value for gamma for now. It's one of the parameters which ideally it's auto-tuned. You need not provide. I just gave it so that you understand the overfitting and underfitting problem. So let me just run this particular code. So all I'm doing here is the training accuracy and the test accuracy. So wait for the results. See, I have a test accuracy of 95% and training accuracy of 98%. The exercise for you is change the kernel functions and C values and see if you can get a higher accuracy percentage. But now let me spend some time. So I'm just going to do one particular code. Next one I will do it in next class. So there are certain things which I want to talk about this code. You know how we have data sets? I send you the data set in CSV and you load it into data frame. So sklearn has its own data set. So in sklearn, there is a package called datasets. So in that data set, there is one data set called iris. Anyone knows what iris is? So iris is this particular flower, that has like petal length, it has like sepal length and stuff. So there is a data set in sklearn. So in sklearn, you import, obviously you import SVM and you also import. So these are publicly available data set which is published in sklearn library. So what I'm doing here is I'm loading that particular iris data set from the data sets. And the data set has data and target. Target is nothing but the Y value. And data is nothing but the X value. So data is all the features. Target is the Y value. So since this data set is in class sequences, right? So if you look at the data set, if I print out iris, so it is all 1 1 1 1 1 1 1 1 2 2 2 2 2. So it's all like in it's all basically in a sequence. So first step, what I do is I shuffle them because I don't want to train on 2 classes and test on the 3rd class. So okay, now is the time I'll actually tell you on how to do the testing also. So clear this. So now you have a data set, right? So now I'm talking of iris data set. So iris. So let's say we have 20,000 samples here or 20,000 observations. And then like first ones are 1 1 1 1 first class. Let's say the 3 classes. 2 2 2 2 2 3 3 3 3. This is the target value, Y value. So how will you evaluate an algorithm? So this is all the data set you have. So how will you evaluate an algorithm? So now I'll say, okay, so Deepika will use RBF kernel, Raghav will use polynomial kernel, Satya will use some other kernel, Meher will use something else, right? So all of you will use different kernel functions or different C values and stuff. But how will I know whose algorithm works the best?
Through testing?
Through testing, right? So we don't have additional test data, right? Like I have a data set, I gave it to you.
So what we generally do is we take, because even in test also, hypothetically test data, we won't know the labels. But to calculate the accuracy of the algorithm, we need to know the label, right? Because once your algorithm says it is class 2, you need to still know what the original value is to say whether the algorithm is correct or not. So generally what we do is we take the data set and divide it into two parts.
Actually, you lost your screen. I mean, I lost your screen. Like, blanked out.
Oh, can't you see my screen?
No.
No one can
can.
see my screen?
I can.
I too can see your screen.
Okay, let me share it again. Raghu, can you see now?
Yeah, now I can see.
Okay. So basically we have this iris data set, which actually has all these observations and target value. Target value is the class label. So when you come up with different algorithms, we need to test the accuracy of that particular thing. And accuracy is only tested on the, accuracy is only got on the test set. So what we generally do is once we have these observations, we divide them into two classes. One is called training class, and other is called test class. So in training, we probably take 80% of the data and give it for training, 80 or 70% of the data. Why do we need training? This training is what will make you what make the SVM decide the decision boundary. So the decision boundary is basically got by the decision boundary is basically got by this particular training data set. So once the SVM decides on this decision boundary, the training is done. So it won't require this data again. But the rest 30%, we use it for testing. The reason is because we know the original labels, right? Because we have the data here. But we pretend we don't know the original labels and we'll give it to the algorithm. We will say, hey, this is the new observation. Please tell me, algorithm, what is the value? What is the class value? So you'll say class 1. The algorithm will say, oh, this is 2, this is 3, this is this thing, and we'll compare it with original values. So we have the 1, 2, and 3, right? So this is what the accuracy depends on. So the algorithm which has the highest test accuracy is the winner, because that's what we will use in real life. So I used the, let me show you. So I got a test accuracy of 95%, and I used simple parameter. I used 1 as the hard margin, 10 as the gamma, and linear kernel. But I think the exercise for you is to try out different kernels and beat my test accuracy. Why is training accuracy 98.11%? Why not 100%?
There's a margin of error, like
Exactly, there is some margin over there. That's because I gave a value of C which is less, right? If you see this, I used a soft margin classifier. When I use soft margin classifier, obviously in the training also there are some outliers. Does it make sense? Because if you look at this is training data, right? All this is training data. In the training data, I'm saying that, hey, please be lenient on this. So even in training data, I don't have 100% accuracy because I'm using a softer margin. So that's why even if you have 1 or 2 on these two sides, it will still give me less. So this is my thing. This is my results. I'm pretty sure, I'm 100% sure there are better results you can get from this thing. But let us go through what we are doing here. So first we load the data, we load the targets. I shuffle them because they're all in sequence. And then there is something called as train test split function in the sklearn model. So what this does is I give the x and y and I say the test size. So I say 30% of it, 0.3 means 30% of it used for testing, the rest of them use it for training. So I take the data, I shuffle them and then I say that, hey, use the split. So what it'll do is it'll put X train, X test, Y train, Y test. 70% it'll do training, 30% it'll do testing. So this is what I've used test train split. So, and then I use my SVM to fit on the train data. So I've created a kernel which is linear and basically having a soft margin of 1 and gamma of 10. And I fit it to my X train and Y train. And then on the prediction, I actually predict on the training data also because I've actually fitted it, right? But the actual prediction is on the test data. So I take X test and I predict what the Y values are. So if you look at it, all this theory you've learned is only this one line. Just for this one line, like the last 2 hours we spent. But you need to, but the thing is, I want you to understand what kernel functions are, what it is doing, what are soft margin classifiers, like if what happens if I change the value of C. So in this particular case for the iris data set, which is there in the thing, my accuracy I got is, so it keeps changing. Why is it changing? In this case, I got 100% accuracy. Why is the test accuracy changing every single time I do this? Any guesses?
It says shuffle.
It's random, right?
Exactly.
Yeah.
It's shuffle. It's random because in one case when I'm shuffling it, it could take like good points in one places. And then this also is random. Train test split, I'm just saying random state is 0. So basically it's picking those things also randomly. So it need not exactly be the same thing as what we are taking every single time. So see, now it is less. But this is how, but overall, right, when you run it like 20, 30 times, you'll get an average understanding of how this accuracy is. So this is pretty simple. I think you can write this. Next one I actually wrote is for multi-class. So this is a simple 2-class classification. But I have one more thing for multi-class classification. So I'll just show you this in visual. So we will write this tomorrow. Next class, we will go through the code of this. But it's pretty much doing the same thing. It is loading the iris data set. And instead of using like linear function, it is using polynomial function of degree 4. And it does this fit. So I just want to show you how it changes. So if I run this, it calculates it for all the boundaries. And I want to, I only took 2 features, say sepal length and sepal width. Sepal means that the petal length. Iris. So you see this polynomial kernel, it's not linear. You see how it is creating this decision boundary. So this decision boundary in some other space, polynomial space, is linear. But when you translate it back to your original space, it looks like this. So you see one class is on this side, second class is in the middle, third class. So there is some misclassifications here. You see that most of the green is, a lot of green is on this side. But this is the best it could do. I'm sure if you change the parameters, if you change the kernel functions, you can get like better results. So even though the data is jumbled here, you see how it is able to predict using different kernel functions. Should I just finish up going through this code also so that you can just play around, or do you want me to do the code again next time? So this particular code is simple, right? So all I'm doing is, I'll send this code tonight. All I'm doing is I'm loading the iris data. I'm taking the target, I'm shuffling it. I'm splitting it into test and train, and I'm fitting a SVM model. And after fitting it, I'm saying, please predict the test results and train results. And I'm just printing out the accuracy. In this particular case, I'm actually reading all the data. So I'm loading the test data, but all I'm actually creating a polynomial function. We'll do this next class. So it's a little bit more involved because I've actually used the 3D plotting with polynomial kernel just to show you this. We'll do this next class, but please try to do this tonight. The first one. The first one is very simple. Load the data, shuffle the data, split the data, fit the model, predict, and give the answer. Is this clear? Is support vector machine clear? Like what it's doing? Forget about the math, like how it does it and all. The only reason I showed the math is for the kernel trick and kernel function. So all I wanted to bring forward is you need not know what the higher dimensional space is as long as you know what the kernel function is. Questions? Is this clear?
Yeah, Sai. Sai, so is there any book that you can recommend for this math behind all this?
Yeah, so support vector machine, there is a really good book in O'Reilly's. I'll send you. In general, artificial intelligence and stuff has there are really involved books. I can send you some PDFs. I have some.
Okay, thanks, Sai.
Actually, I did download. I mean, the material was prepared from those PDFs. Let me see. Support vector machine. Multi-classes. So, yeah, I downloaded the PDF from that O'Reilly's chapter. I can send you these if you guys are interested in.
Yeah, that'll be helpful, Sai.
Yeah.
So it'll talk about. It talks about all these kernel functions and stuff. Yeah, I'll send you these PDFs also if you want. If you're interested in going through the math of it and how it works, but it's pretty much like what I've actually created the slides from this only. So you see the soft margins, hard margins. It'll be difficult to follow if you just read this. I try to like simplify it as much as possible, but I'll send you the PDFs as well to understand. But trust me, like 90% of the people don't really know what is happening. As long as you know, when you change hard margins, when you change kernel functions, you get different results. But you can read up more on RBF kernel. RBF kernels are very, very popular. So instead of linear kernels, radial basis functions, that's the kernel which is being used very popularly. So I'll send this particular data.
So RBF, you'll be doing it in the next class, is it?
No, I mean, I didn't think of like it's just a kernel function, right? So
Okay.
I thought you could just change instead of giving linear or polynomial here.
Okay, just like that. Okay.
Yeah. So okay, yeah. So RBF you can just try. I mean, but then I think it'll be a good reading to actually, if you want, I can like tell you what the kernel function is. RBF, another kind of kernel function which gets fit into like support vector machine and stuff. So kernel methods, kernel tricks and stuff. But they're all very math intensive. So I was afraid that I might lose them, and I'm explaining all that. So I put it on a slightly lower this thing. But if I want to go, I can talk about Kern-Tucker condition, Mercer's condition, how Lagrange multipliers work, and how Lagrange multipliers ensure that only the support vectors are used and stuff. But I didn't want to make it that complex. I thought this would be a brief overview of like how support vector machines work, like what projection to higher dimension spaces, and this visualization will help you understand. The one which I showed you, right? Like this case, even though the data is not separable, there's an iris example. So you see that how it's creating that nonlinear boundary. So you can actually plot the same thing by changing the kernel. So here instead of polynomial kernel. So I would say that every time when you're doing this, please read the documentation on these things. So if you go through the sklearn website, they'll give you documentation for every parameter which you're sending. So if you want to try out other kernels, you can just see the sklearn website's kernels and you can try out different kernels and plot. This plot will tell you how it is changing. So maybe if you use RBF kernel, it might have a different, different margins and stuff. But the key takeaway is like even though the data is non-linearly separable, SVM will actually help you to separate them by using kernel functions. So is that clear?
Yeah, Sai.
Yeah.
Okay. So I think that's it for today's class. Next class we'll talk about cross validations. Then we'll talk about the overfitting, underfitting problems. We'll talk about how do you like different testing method, leave one out method, k-fold method, and stuff like that. And we will do one. So as I said, right, this is the most complex of machine learning algorithm. We'll do a very simple algorithm called k nearest neighbors next time. It's called KNN, k nearest neighbors. So we'll do that for next class. So, all right, I'll share this code and just do the first code. Next one we'll do in the next class. So the first one is very simple. Just take the data, shuffle it, divide it into test, train, fit a model, predict. That's all. Okay.
Thank you.
Sai, I won't be able to attend the next class.
On Sunday?
Yeah.
Okay. So I will. Is the recording
Yeah.
going to help?
Yeah, I think that should help. If I have any doubts beyond that, I can just...
So if you have doubts, right, I can start the class 15 minutes early.
Okay.
We can discuss the first 15 minutes about the doubts and stuff. But
thanks.
Yeah, no problem.
Okay. Thanks, Sai. Okay. Yeah.
Bye.
Bye.
Bye.